You see, it is a very common human experience. You are walking down the street. Perhaps you are thinking about what you will have for dinner. Or maybe you are thinking about why the electron has a negative charge. It does not matter. Suddenly, the sky opens up, it begins to rain. Now, your instinct, the one that has been hardwired into you by millions of years of evolution, tells you to do one simple thing. Run. You think to yourself that if I can just get from point A to point B faster, I will spend less time in the rain. And if I spend less time in the rain, I will get less wet. It seems perfectly logical. It seems like common sense. But I have to tell you something. Nature does not care about your common sense. Nature is imaginative. She is subtle, and she has set up a trap for you. Today, I want to take you on a little journey. We are going to look at something as mundane as getting wet in a rainstorm, and we're going to find that hidden inside. This simple problem is the key to understanding how we collide with the universe itself. We are going to talk about geometry, we are going to talk about time, and we are going to talk about why running might just be the most foolish thing you can do. Before we break reality, make sure to subscribe. This is not just physics. This is how the world works. Let us start with the illusion. Why do you think running saves you? Because you are thinking about time. You are thinking that the rain is falling down on top of your head, and if you stand there for 10 minutes, you will get soaked. If you stand there for 1 minute, you will only get a little bit wet. This is true. This is the vertical component. Imagine the rain is not water, but small blue marbles falling from the sky at a constant rate. If you have a bucket on your head, the longer you stand there, the more marbles fill the bucket. So logically, you say to yourself, I must minimize the time, I must run. But you are forgetting something fundamental. You are not a 2D line. You are a 3D object moving through space. You have a front, you have a chest, you have a face. When you stand still, the rain falls straight down. It hits your head and your shoulders, but your face remains dry. Your chest remains dry. Now, what happens when you start to move? Suddenly, relative to you, the rain is no longer falling straight down. It is coming at you from an angle. It is hitting you in the face. You have created a wall of water, and you are running smack into it. Think of it this way. Imagine the air in front of you is a long hallway, and suspended in this hallway are millions of these blue marbles frozen in place. They are not moving. They are just hanging there in the air. Now, you have to get to the end of the hallway. Does it matter how fast you run? Think about it. Whether you walk slowly or whether you run like a sprinter, your body has to sweep out the exact same volume of space. You have to push aside the exact same amount of air, and therefore you have to collide with the exact same number of marbles. If you run twice as fast, you hit them twice as hard, and you hit them in half the time. But the total number of marbles you hit with your chest is exactly the same. This is the paradox. The faster you run to save your head from the vertical rain, the faster you smash your chest into the horizontal rain. You are essentially acting like a snowplow. So now we have a fight between the top of your head and the front of your chest. One wants you to run, the other says it does not matter. Who wins? To understand this, we have to go back. We have to look at how the giants of the past tried to solve problems of motion. Think of Galileo. Think of Newton. They looked at the world, and they tried to break it down into components. This is the secret to classical physics. You cannot solve a complicated problem all at once. You have to chop it up. Newton would say, let us look at the raindrop. It has a velocity vector, a fancy word for an arrow pointing down. When you run, you have an arrow pointing forward. But because you are the one observing the rain, from your perspective, it looks like the rain has an arrow pointing backwards and down. If you run fast enough, the rain looks like it is coming straight at you horizontally. Have you ever driven in a car in a rainstorm? The rain does not hit the roof as much as it smashes into the windshield. The faster you drive, the more horizontal the rain becomes. So here is the triumph of the old physics. We can calculate this. We can say that the total wetness is the sum of two things. First, the wetness from above, which depends on time. Second, the wetness from the front, which depends on distance. Since the distance to the nearest shelter is fixed, say 100 meters, the amount of water waiting for you in front of your face is fixed. You cannot change it. It is a wall of water waiting for you to walk through it. The only thing you can change is the wetness on your head. So, the Newtonian calculation says, run. Run as fast as you can. Minimize the time, because the distance cost is already paid. But wait, is that the whole story? If that were true, why does it feel so wrong? Why, when you run in a heavy downpour, do you feel like you are getting soaked to the bone instantly? There is a flaw in our simple model, a crack in the logic. We are treating you like a geometric point, but you are not a point. You are a complex shape, and the rain is not just arrows. It is a fluid. It splashes. It bounces. And more importantly, we are assuming the rain falls vertically. But in the real world, there is wind. There is turbulence. However, even if we stay in the ideal world of physics, there is something deeper going on here. Something that connects this simple rain problem to the very heart of how we understand the universe. It connects to how we understand atoms and how we understand light. Let us dive deeper. We need to stop thinking about rain and start thinking about flux. In physics, when we want to understand how particles interact, like when we smash electrons together or shoot alpha particles at gold foil, we talk about the cross-section. Imagine you are a target. The rain is a stream of bullets. The cross-section is basically how big of a target you are. When you stand still, your cross-section to the falling rain is just the top of your head and shoulders. It is small. When you move, you are effectively tilting your cross-section. You are exposing your entire front body to the flux. Now, imagine we take a slice of space, just a thin slice, and we look at the density of raindrops in that slice. It is a constant number. Let us say there is 1 drop per cubic inch. When you move through this, you are sweeping out a volume. This is a geometric reality. It is inescapable. Volume equals your surface area times the distance. V equals A times D. Notice something missing? Time is not in that equation. Speed is not in that equation. This is the zero-sum game of the horizontal wall. No matter how fast you go, you hit the same horizontal water. So, if the horizontal water is fixed and the vertical water decreases with speed, the answer should still be run infinitely fast, right? Well, let's look at it like a physicist who cares about the limits. What happens if you run at the speed of light? Aside from burning up due to friction, which is a practical problem, think about the geometry. The rain is falling. You are moving so fast that the rain effectively looks like it is standing still horizontally. You hit every single drop in that tunnel of air instantaneously. But here is where it gets interesting. What if you lean forward? When people run, they do not run like stiff boards. They lean. Why do they lean? To balance? Perhaps. But look at the geometry. When you lean forward, you are actually hiding your chest underneath the umbrella of your own head. You are reducing your cross-section. If you could lean forward perfectly horizontally, like Superman, so your body is parallel to the ground, and then you flew at super speed, you would minimize your wetness dramatically. Why? Because you have reduced your frontal area to almost zero. You have turned yourself into a thin line cutting through the field. So the answer is not just run. The answer is change your geometry. This brings us to the profound realization. The interaction with the universe depends on your orientation in space. It depends on the angle at which you slice through the field. This is exactly what happens in electromagnetism. It is exactly what happens with light. The amount of interaction depends on the angle of incidence. But I promised you we would go deeper. We need to talk about time. Because rain is not just falling in space. It is falling in time. In my lectures, I often talk about space-time. Not space and time. Space-time. One thing. A 4-dimensional blob. Imagine a sausage. A big, long salami sausage. you can slice this sausage straight down and you get circles. That is one way of looking at the universe. That is now. But if you slice the sausage at an angle, you get ovals. You get a different cross section. When you run, you are essentially tilting your knife. You are slicing the sausage of the universe at a different angle. Let's visualize the rain in space-time. Imagine a piece of paper. The vertical axis is time. The horizontal axis is space. A raindrop sitting still on the ground is a vertical line moving up through time. A raindrop falling is a slanted line. It is moving through space and time. Now, you are also a line in this diagram. If you stand still, you are a vertical line moving through time. You intersect the falling rain lines at a certain angle. When you run, you tilt your line. You are changing the angle at which your world line intersects the world lines of the raindrops. This is special relativity in a rainstorm. The amount of wetness you experience is the number of intersection points between your world line and the rain's world lines. Now, here is the mind melt. Here is the thing that keeps physicists awake at night. We assume that the rain is there whether we hit it or not. We assume the drops exist in the tunnel even before we run through them. We assume that reality is a stage and the props are set up waiting for the actors. But in quantum mechanics, and in the way I like to look at the world, can we really say the drop exists if we don't interact with it? This sounds like philosophy, but it is physics. The only thing we can measure, the only thing that is real, is the click of the detector, the splash on your shirt. That is an event. The universe is a swarm of potential events, a swarm of probabilities. When you decide to run, you are making a choice to sample the universe in a specific way. You are choosing which events to make real. If you walk, you sample the vertical events. If you run, you sample the horizontal events. You are not just a passive victim of the weather. You are an active participant in determining which raindrops become part of your reality. Think about the emptiness of atoms. Atoms are mostly empty space. If the nucleus was a peanut in the middle of a stadium, the electrons would be flying around the nosebleed seats. You are mostly nothing. The rain is mostly nothing. So why do you get wet at all? Why doesn't the rain pass right through you? It is because of the electric fields. The electrons in the water repel the electrons in your skin. It is a force field pushing against a force field. When you run into that wall of water, you are smashing force fields together. Now, let's zoom out, way out. If speed changes how we interact with rain, does speed change how we interact with time? Yes, it absolutely does. If you could run fast enough, really fast, close to the speed of light, the rain would stop falling. Time for the rain would freeze relative to you. The drops would become suspended streaks of energy. But for you, inside your running frame of reference, your clock would tick normally. This leads to the twin paradox. But forget twins. Think about the wetness. If you move at the speed of light, you shrink the distance to zero, the hallway becomes flat, you are instantly at the destination. You hit all the horizontal rain in 0 time. But because time has stopped for you relative to the rain, you hit 0 vertical rain. So the ultimate limit, the absolute truth of the universe, suggests that if you want to avoid the time penalty of the vertical rain, you must move at the speed of light. You must become a photon, but you are not a photon. You are a blob of biology. You have mass, and mass hates to change its state of motion. Mass resists. So here you are stuck in the middle. You cannot move at the speed of light. You cannot teleport. You have to trudge through the mud. So what is the answer? Should you run? Mathematically, yes. If you run, you eliminate the vertical rain. You hit the fixed wall of horizontal rain, which you would have hit anyway eventually, but you compress that wetness into a shorter time. You get the pain over with quicker, but there is a catch. There is always a catch. When you run, you splash. You kick up water from the ground. Your feet smash into puddles, sending shock waves, mini tsunamis that throw water up onto your legs. We forgot the ground. We looked at the sky We looked at the air, but we forgot the chaos beneath our feet. This is the lesson of physics. You can build a beautiful model. You can draw your vectors. You can slice your space-time sausage. But if you forget the mud on the ground, you are going to get dirty. Feynman's rule of running in the rain is this: run, but do not run so fast that you trip. Because if you trip and fall into a puddle, the geometry doesn't matter anymore. You are 100% wet. And that is a pretty good metaphor for life, isn't it? We are all rushing. We are all trying to minimize the wetness, the pain, the delay,